Welcome back, everybody. I hope you are ready. So this is the last session of ISLA 2022. So we have our first student speaker, Jaskirat, and along with his group members, Nitish and Neha. Okay. So all of you will be presenting?
Yes.
Yes. So that's 25 minutes in total. Okay. So over to you.
So am I audible?
What's your topic?
Model logic.
Model logic. Okay. Dualities for model logic, right?
Yes.
Okay, good.
So just to confirm, am I audible to the online audience as well?
Yes.
Okay. Thank you. So today I will be starting with model logic. So we all have already seen what is propositional logic and first order logic. So if this is my first order logic, we know that propositional logic is a part of first order logic. It explains certain things, but first order logic goes ahead and explains more things. So what model logic is, it is something more than propositional logic, but less than first order logic. Model logic lies between propositional logic and first order logic. So this is the starting of model logic. Propositional logic starts with basic statements such as grass is green or sky is blue. Model logic goes one step ahead and allows us to introduce modalities into the propositional logic. So we can say certain statements such as it is possible that grass is green. In the future, grass will be green. It is necessary that grass is green. So we are allowed to introduce modalities into the simple statements. So if this is my propositional logic, it was propositional variables, then P or formulas if they are alpha or beta, then we have not alpha, and then similarly we can define and implication. If this is my first order logic, which is and T1, T2 till Tn, and we have here also alpha or beta, not alpha, and we also have extra thing here is there exists xi alpha, and similarly the dual of this for all xi alpha. Model logic lies in between them. So model logic, we have the propositional variables just like PL, we have alpha or beta, we have not alpha. We have a new unary modality here which is known as diamond alpha, and similarly dual of this box alpha. So this is the dual of this. So box alpha is nothing but not of diamond, not alpha. The modality diamond here means that it is possible that alpha, and box here means that it is necessary that alpha. So we can visualize this, that it is necessary that alpha can be also read that it is not possible that alpha is not there. So it means that it is necessary that alpha is there. So this is box alpha and not of diamond, not alpha. So moving forward, what model logic is applied on relational semantics. So model logic is applied on relational structures, and there are valuations and valuations and logics on relational structures, which is known as the further model logic. So how do the relational structures look like? The basic of relational structure is a world. So this is our free state or state where we will be evaluating things like P is true here or not, alpha is true here or not. And there are other worlds as well, W1, W2. And these are all connected together. These are relational structures. So there are relations between them. We say that if P is true at some world which is related to my world, then we say that diamond P is true here. Diamond P basically means that I have a related world where P is true. Similarly, if all the related worlds to my world, in all my worlds, if P is true everywhere, then I say that box P is true at my world. Now, in 1969, around 1959, in the eras of 1960s, Kripke introduced what is known as Kripke frames. So Kripke frames are what is known as the relational structures. He defined them. So a frame is a collection of words and relations. So here the word set of words is not empty. There must be at least one word, and then relations is a subset of W cross W. Basically, my mappings of words is in this relational set. Now, this is just a relational set. This is just a frame. How do we introduce valuations? We introduce valuations into this, and this is known as Kripke model. So we have a frame and valuations here, where valuations is a map from, just like in PL, we have propositional variables to power set of words. Or this, why is this true? Because valuation of any P is a subset of W. Basically, what is my P? If P is true at some, I have a few words, and P is true at certain words, then valuation of P is basically the set of those words. So V maps from PV to power set of W. And this is the valuations. Now, how I will write the representation of what is true for a formula. Like I say that in my model M, at a word W belonging to the set of words in that model, if alpha is satisfied at that W, then that is written as M, W double turnstile alpha. Now this double turnstile is a little different notation from what we use in PL. There we use this notation, but in model logic, Kripke generally uses this kind of notation. So I will be also using this notation. This is commonly used in model logic for double turnstile. Now I will define this. How is this defined in model logic? Recursively, just like it was defined in propositional logic, recursively. So basically, we will initially start with P only. So when do we say that this is true at a certain word in the frame? If and only if P belongs to valuation of, if and only if W belongs to valuation of P. This is the basic simple case where we have a P. Then by induction, we assume that MW double turnstile alpha is true. Now, when will this be true? Double turnstile not alpha, if and only if model word double not alpha. Similarly, for alpha or beta and alpha and beta can be seen just like in propositional logic. Now I will show what it means for diamond alpha to be true at W. So this is if and only if there is a W dash, there exists a W dash belonging to W such that W related to W dash and model W dash double turnstile W dash double turnstile alpha. So it does not matter whether alpha is true, satisfied at W or not. What we are seeing here is if there is a W dash which is related to my word and W at that W dash alpha is satisfied, then I say that diamond alpha is true. Similarly for box alpha, if and only if, here it is a little different. If there is a W dash belonging to W such that W related to W dash, then at W dash alpha should be true. Now here we can see that a little vacuous argument can also come in. If there are a few words and my word is not related to any other word, then I can say that box alpha is true here. Basically because there is no word which is related to my word. So by vacuous argument, box alpha is true here at this word. So just to make things more clear, I can give an example here. Okay, so 1 minute.
You have finished 8 minutes.
Just a minute. Last example. Assume that this is my frame, and in this frame, W is the set of W1, W2, W3, and W4. Okay. Relation is this: W1, W2, W2, W4, W3, W2, and W3, W4. For simplicity, let's take only one propositional variable P belonging to PB, such that in this valuation of P is W1 comma W2. So this is, I have written mathematically the frame and value model, because I have written valuations as well. So now let's draw the diagram. W1, W2. Here, according to the mappings, these are the mappings. Now we can see that P is true here, P is not true. Here we can see that diamond alpha is true here, diamond P is true here, diamond P is not true here, diamond P is true here, and diamond P, diamond P is not true here. And I hope it is seen that how these are related and how it is not. And here box P is true, here box P is not true, here box P is not true, and here box P is true by vacuous argument. So in this case, we can clearly see how P can be true, but box P and box P are also true, not true. I mean, different cases can exist at the same time. Okay, you can continue.
Yeah, next to Nitish.
I'll try to hurry along. So like this is the model logic, and like in propositional logic we had a system of axioms and some rules to follow along with it. Am I not audible? Where's just okay. So we had some rules to follow along with it. So we can build various systems in our model logics like that. And one of the system I would like to talk about is our K logic, same by Sol Kripke. So K system of models. So like in this system, we have some axioms. So these axioms are and which he wrote already, and there we have some rules of rules for obviously the modus ponens, because we are building based on the propositional logic. Then we take generalization, meaning if we have phi, then we guarantee that delta phi is true also. Then we consider something that is known as uniform substitution, in which we, for a formula, like we have some formula phi, and we can replace its propositional letter by sequentially, and we can convert into some other formula that is valid in that model, but it's not the same. That's something a uniform substitution. Now, and I will revisit our two definition or definition of morphism. Like I know that these things are feeling that they are distinct, but they come to some nice picture. Our morphism for a category. In a category, it is a map between its two elements, like A to B, F of or precisely, if I want to say, then it's a class home of C. The class of which means source object is mapped to a target object B. And further now I will go for functors. Functors are mapped between two categories such that they are gonna follow our two conditions. For like if our functor is F, some C to D, then it will follow this F IDX equals id f of x and our f of z into f of x. Now, in our previous lectures on propositional logic and stone duality, we saw that how propositional logic connects it to. So like we had this diagram where we had our stone spaces and we had our Boolean algebra. They both were duals to each other, right? So if they both were dual to each other, we can say PS barabar 1x, 1x and SP barabar 1a. Of course, they are naturally isomorphic. And in model logic, we extend this stone duality. So for this, what we do, is it visible? Okay. I'm afraid that I'm getting in the way. So, like we have a set of spaces X, category of spaces S, and we have a map, and this is our algebraical. This is our algebra. And now what we do, we define a functor on it, which maps X to X, and we define this functor. This is T. Right, I'm not going into the derivations or like details. I just want to present the idea behind it. So, like this is L represents the algebraic semantic of model algebra, and this is the or we can say the whatever happening in this but whatever the transformation going between them, and this represents transformation going between them. So we can find many classes of, and these transformations are based on our model algebra that follows that suppose that it follows our case system. There can be various system too. So it follows our model algebra, and there comes a nice result which leads us to if and only if our model algebra is sound and complete, then these two will be dual to each other. Our T and L will be dual to each other, which gives us a very nice relationship. If we have two, if we can prove somehow that we have a mapping between them on this model algebra, then we can prove that our model algebra is complete and sound, and we don't have to do anything other than that. And there were some more nice results here. This is a dual to V, and we call, like, I'm running out of time. So these are called as V coalgebras. And there was one result I would like to mention, that there is an S4 system, and same way we can prove it, that it is model logic for all our topological spaces that we can construct. Yeah. So, and there is
your group has only 8 minutes left.
Yeah, sorry about that. Like, it was very interesting topic, and I would have liked to cover it in more detail.
Okay, thanks. Thank you. Neha, are you ready?
Yes, sir. Yes, sir.
Okay, please start.
So, it says that host disabled the participant screen.
Can you speak a bit louder?
Actually, it says host disabled participant screen sharing. I can't share.
You are sharing your screen already.
Why I can't share this?
Disable hai.
Yes, someone is sharing the screen, Amit. So
Gauri Nevada is sharing.
Yeah, it was enabled for everyone.
Okay, okay, okay.
Please share it again. You had shared it earlier. Okay, yes.
Sorry.
You have got only 8 minutes left. Please start.
Okay. So hello everyone. So the topic, am I audible? Am I audible?
Yes, yes, you are.
Okay. But I want to share. Okay. Wait.
You are sometimes audible, sometimes not.
I want to share.
You have shared it. We can see your slides.
Actually, I want to on the video, switch on the video, but
We can see your slide titled Duality in Modal Logic.
okay, okay. So I will start. So main topic is duality in model logic. So by duality, what we really mean in a categorical sense, we have two categories C and D. We say C and D are dually equivalent if we C and D of are equivalent. That is, we have some contravariant functors linking C and D. Okay. So here the main characters are model algebras and cryptic structures. What our main purpose is to form such contravariant functors between them. So we will start by some basic definitions. Model algebras. So model algebras are basically a Boolean algebras with additional model operator which preserve the additive property and the normality property. Okay. So how will we define a morphism between model algebras? It is defined like this. Uh, if a morphism between two model algebras is a model algebra morphism if it preserves all the Boolean algebra morphism and additional the model operator morphism. Simply, eta of f of a is equal to f dash of eta of a. Okay. So Kripke structures already this had defined. It is a set with a binary relation, and now we are going to define what is a bounded morphism. If you have a morphism between two cryptic frames, we say it is a bounded morphism if it's preserve the main two properties, basically, namely, we say fourth and back properties. By fourth, this will imply that if x is related to y, this will imply fx is related to fy in s dash, and by back, we mean if fx is related to y dash in s dash, this will imply if we have some y in s such that x related to y, and f of y is equal to y dash. Okay. So complex algebras. So actually, there is a whole theory behind all this complex algebra. I have just taken the simplest definition. Complex algebras behaves like a tool. How we are going to embed an algebra to a frame. Oh, sorry, a frame to an algebra. Okay, so for a given frame, its complex algebra, it is an extension of the power set algebra with an additional operation MR, where MR is defined as it is the collection of all those points of S which is related to some point of X, where X is an subset of S. Ultrafilters frame are the same tool. How complex algebras give us the embedding from frame to model algebra. Ultrafilter frames give us the embedding. I can't say embedding, but how can we send a Boolean algebra with an operator to an crypto frame? So it is defined like that. If we have a Boolean algebra with an operator f, then the frame collection of all ultrafilters of U within relation QF is called the ultrafilter frame of U, where QF is defined by U QF related to U1 if and only if FA is in U for all A in UN. There is an alternate way to define such a relation, which is defined as UQF related to U1 if and only if negation of f of negation of A is in U. This will imply A must be in UN. I have defined this definition because I'm going to use this definition in a very important theorem, Johnson-Tarski theorem. This says every
You have
Boolean
got
algebra.
2 minutes left, Neha.
Oh. So can we extend 2-3 minutes?
We have very tight schedule because at 4 o'clock we have to start the closing ceremony. So please try to wrap it up.
So this says every Boolean algebra with operators is embeddable in the full complex algebra of ultrafilter frame. So I have given this just a sketch. We have already this mapping in stone representation theorem, where we have seen that this mapping is already in Boolean embedding. Next, to show that it is a model homomorphism. We can easily show by left to right it just by definition, and from left to right we will just form such a set which will satisfy such condition. Okay, so we can show that by this, and now we have this theorem. If we have a K' with 2 frames and we do that with 2 Boolean algebra with operator, and if beta is a bounded morphism between these, then the morphism sending complex algebras of K dash to complex algebra of K is a model morphism. And if we have a model algebra morphism between 2 Boolean algebra, then the mapping sending ultrafilter frames of U dash to U ultrafilter of U is a bounded morphism. Okay, so I have given a proof first. Okay, so actually it is an easy proof. If we have a bounded morphism, we have defined a mapping in such a manner. Actually, it is an inverse image of such set. Okay, so we can prove easily that beta plus is an Boolean homomorphism by just easy calculation. And for model homomorphism, we can prove by it has the property of bounded morphism. It has back and forth properties. So for left to right inclusion, we will use the forward condition, and by that we can show that left is included in right, and by using the back property we can show that right is included in left. So that's why we will got this equation, like this will hold this property. So that's how we can show that beta subscript plus it's a model algebra homomorphism. For the second, I have just defined the mapping. It's the same mapping, and we can easily show, can't say easily, but actually ultrafilters to ultrafilters normally we can show, and fourth property is easy by using this definition. And for back property, we have to use the we have to construct the set like we have used in Johnson-Tarski theorem, and by using that we can construct a set. This will which will hold that property. Okay, so by which we can show that eta subscript is a bounded morphism. So if we take the class of all cryptic frames with the morphism like in the categorical sense, so then we are just we have this functor actually.
Please wrap up, Neha. Yeah, your time is up.
Contravariant functor. Thus, we have a contravariant functor from cryptic frames to model algebras, and in the same sense, we have a contravariant functor from model algebras to cryptic frames. Thank you.
Thank you. Thanks to all the group members. Nick, do you have anything to say?
No, I enjoyed the presentation very much. It's a pity that they had to rush, but it was very nice.
Thanks a lot, Nick, for being here. Yes, now the next presentation will be Algebra Topological Dualities Survey by Chandra Mohan.
In mathematical, the duality is a translation of a concept or mathematical structure.
Is somebody speaking from the audience? Okay.
The duality in mathematical in mathematics, the duality is a translation of concept or mathematical structure from one structure to another mathematical structure or concepts. And the duality, the first time the duality is defined by Gergoni in 1826. In 1826 for projective geometry, and the duality is defined as the 2 point can give a line and 2 line can give a point. And after that, the Poincare also study the duality for homology, structure of homology and cosmology group of monoids. And after that, there are many other dualities are studied, just like Alexander dualities, and also we see in last 2 and 3 days the stone duality, and also the Marcus, Professor Marcus tell us about the a duality from a spectral space to bounded distributive lattice. But now I am going to discuss about the D varies duality. And this duality is defined between the compact category of compact Hausdorff space and category of D varies algebra. And the D varies algebra is that a complete Boolean algebra with a relation known as proximity. And this relation, if we have any Boolean algebra B and we have a relation this on this, and this relation satisfy some condition like that, if we have 2 elements A then one is always related to this, and second is that if we have 2 elements A and B related by this relation, then this implies that A is always less than B. And third condition is that if A is less than B and related with C is less than D, this implies that A is always related with D. And fourth condition is that if A is related with B and C, then this implies that A is also related with meet of B and C. And fifth condition is that if we have any 2 element A and B that are related, then there exists some C such that A, C and B. And last one is that if B is not equal to 5, not equal to 0, then there exists some element A such that A is related with B or A is less than B. And any completely Boolean space satisfying this proximity axiom is known as D varies algebra. And now we are defining D varies morphisms. If we have a map that from a D varies algebra to another D varies algebra, it's said to be D varies morphism if it preserve 0 And second is that it preserves meat. And third is that if A is related with B, then negation of P of negation of A is always less than B, image of B. And last one is that V of B can be written as join of all P of A such that A is less than B and A belong to our algebra. Any map satisfying this is known as D-varies morphism. And X star that is equal to R of X. X star is a D-varies algebra. Here R of X is a collection of all regular open set in X, and this is a proximity relation on this, and R of X is complete Boolean algebra. Now let and this relation on R of X is defined as if U is related to V and U is any regular open set of X, then if and only if closure of U is always subset of V. And X star is D-varies algebra. Now we are going to taking the categories of, first we are taking the category of Hausdorff, compact Hausdorff space, that is denoted by K house, and the DAV is here for the category of all D-varies algebra. Now we are going to construct some functor between the category of compact Hausdorff and D-varies category of D-varies algebra. So if we have a function from X to Y is continuous, then F star be a function from X star to Y star to X star, such that F star of U is equal to interior and closure of F inverse U, and then this F star satisfies the condition of D-varies morphisms, and this D-varies morphism is produced a contravariant functor.
Yeah, 5 minutes left.
Okay. From K Hausdorff to D category of compact Hausdorff, and D category of DLE varies algebra, and it is denoted by this. And or we can see that if we have K Hausdorff, to D vary algebra, a functor like this, and an object X corresponding this we get X star by this functor, and Y star, and F is a continuous function from X to Y, then we get a F star by this functor, and which goes from Y to X star, and this diagram commutes, so we can say that this is a contravariant functor. Now we are going to define a contravariant functor from D vary algebra to category of compact Hausdorff. And let any D vary algebra that belong to this category and a set S which is subset of D vary algebra, then we define a set of ends of algebra for S that is denoted by all the element of this algebra such that B related to A for some B belonging to S, and any filter that satisfy the end set of algebra is equal to that filter is known as maximal proper round filter. And so now we are considering a map rho from a D vary algebra to another D vary algebra is isomorphic.
Chandramohan, you can try to wrap up now.
This is last step.
Okay.
And then there exists another map that is denoted by P star such that and the Y of this algebra and Y of this algebra, which is denoted and which is defined by their P of Y, P star of Y is equal to the end set of algebra of P inverse for the P inverse Y, and here the Y mu is denoted for or the topology that is defined by this algebra by using some sets that I am not describing here, and from this we will see that there is a functor. This map introduce a functor that is denoted by blank by star from D vary algebra to a category of compact Hausdorff spaces, and this is a covariant functor. From this we conclude that the compact Hausdorff category of compact Hausdorff species is equivalent to, or we can say that duly equivalent to the category of D vary algebra. Thanks.
Thank you. So let's clap for Chandramohan. We are getting many more examples of dualities in the school titled Logic and Dualities. Next in our stop is
could I ask Amit, yes. Could I ask one quick question? Sure. What source was used for this?
What did you refer to?
Which reference?
I used a paper whose name and an extension of D varies duality to completely regular space. I used a paper whose title is an extension of D varies duality of completely regular space and compactification.
Okay, thank you.
And written by G. Bejan Savli.
Yes, that's my brother Guram.
For introduction part, I using the little bit from the Wikipedia and history of algebraic topology, duality of algebraic topology.
Okay.
Okay, thank you.
Thank you. Right. So next in our list are two youngsters, Manan and Lavesh, and they are going to talk about completeness theorem in propositional logic.
So hello everyone. I will be presenting on completeness of propositional logic. I'll first prove through method of resolution. Then Manan will give a more formal proof for the completeness and soundness theorem in propositional logic. So starting with there are few definitions. So first there is literal. Literal means any atomic statement, atomic variable and its negation. Then we have clause. Clause is just set of literals. So any literals, P, negation, Q, or anything. Then we have set of clauses. Then we have set of clauses. Set of clauses can be like P, comma Q, then negation P, comma Q. So starting with, I'll state one lemma, maybe that any formula can be written as set of clauses, meaning like if there is any formula, we will first draw its truth table, then we'll try to write it in its CNF form, like something of this form. Like any formula can be written in this way using the truth table of the formula. And this can be written in as set of clauses. Like this can be written as P comma Q, then negation P comma Q. Okay. So if any literal is true, like in this statement, if any literal is true, then we'll say the clause is satisfiable. If P is true, then we can say the clause is satisfiable. Like P and Q will be written this way, like P or negation Q in this. So, so to prove the soundness theorem first, I'll do a bit of construction. So C1 is one clause and C2 is another clause. And C will be called its resolvent if like C1 has a formula P and C1 has negation P. And there can be other variables. In C, we'll not take P or negation P, we'll take other formulas and their union. Like C will be union of this minus P, then union C2 minus negation of P. So it is not very hard to see that if C1 and C2 are satisfiable, then C will also be satisfiable. Like without loss of generality, I'll show one way, like if P is true, let's assume, this will be 0. Then since C2 is satisfiable, any other variable in this will also be true. And this variable will also be in C because we are taking union. So C's will also be satisfiable. So now to prove the soundness theorem, like this, using this, we'll try to prove the soundness theorem. So like if, so we have proved that if C1 and C2 are satisfiable, then C is also satisfiable. This way we'll try to create a tree in which C can be derived from C1 and C2. So if there is any formula which we can derive from other statements, so here can be C1, C2 and C3, and this is our like resolvent. So if C is derived from C1, C2, and C3, and C1, C2, and C3 are satisfiable, then C will also be satisfiable. This proves the soundness result in some way. So next we'll try to prove the completeness. We'll also do one more construction, like similar construction to prove the completeness. So I'll make one thing. Cp is equal to true. So what is this? First we have a set of clauses C. It can have like many small clauses. Then it can also have negation P and some other formulas and other formulas. So to write Cp is equal to true, I'll first remove all those formulas which have P in them. So I'll not take this into consideration. And those formulas which have negation P in them, I'll take them but remove the negation P from them. So you can see if C is satisfiable, and I extend the valuation by including P to be true, so C will also be true. Like if P is equal to true is satisfiable, then I'll extend the valuation including P to be true, so C will also be satisfiable the same way, because this formula remaining is satisfiable. I do not care about negation of P, and P is here is true, so this will also be true. This way all other like clauses will be true in C. So another way, similar way, I'll create C P is equal to false, which would, for whom I'll not consider the term which have negation P, and I'll remove P from the term which have them. So this is again, I'll for this, if this is satisfiable, I'll extend the valuation including P to be false, and this will make this to be satisfiable. And like how will we use it to prove completeness? So first there is one lemma which says if C P is equal to true is satisfiable, if and only if C is satisfiable. So we have seen the one side of the proof. Other side also goes the similar way, like if C is satisfiable and P is true in C, then I'll remove, like I'm already removing this term, P is true, so negation P is false, so some other literal in this will be true, which will make C P is equal to true to also be true. So now to prove the completeness theorem.
I have a question. So what reference are you using here? I've never seen this proof before.
These are from one lecture, like from some lecture.
Okay.
Like it is not very long, like now I'm finished, then Manan will give one formal proof of this.
Are you going to present alone, or Manan
No,
is?
Manan will
Okay.
present. So now to prove completeness, it will again be proved using induction. Induction on proposition, like these clauses. So let's assume like on literals, like if I have some literals P1, P2, P3 up to Pn. Okay, then first I'll state the completeness theorem. It says that if like I'll prove it using contrapositive. So if C is unsatisfiable, then I can derive empty clause from this. Empty clause is represented through this like box. So I can derive like using like the construction of tree, can derive this from C. So first I'll assume that for P1 up to Pn, I've already done this. Then I'll include Pn plus 1. So C Pn plus 1 equal to true, and C Pn plus 1 equal to false. So now C contains up to like Pn plus 1. C contains Pn plus 1 literals. So now I'll use that lemma that I just stated, that if C Pn plus 1 is true, so I can extend the valuation such that C is satisfiable. But since like, using that, if C is unsatisfiable, So C Pn plus 1 is also unsatisfiable. I'll use like that way to prove that, to prove the using induction the completeness.
You have 1 minute left.
I think we are done with the proof. Like Cpn plus 1 is true. Then like we have assumed like it is true for Pn plus 1 because we are using induction, so we can derive empty clause from these using the resolvent way. And if we can derive empty clause from this, now we have derived empty clause from Cpn plus 1 equal true and Cpn plus 1 equal false. Now if I'll go back to C, I'll have to add Pn plus 1, this literal. But if I'll add Pn plus 1, the worst case scenario will be that I'll be able to derive Pn plus 1 and negation Pn plus 1 from these. And if I'm able to derive this, then I can derive this empty clause from these. Like I'll have to remove P and negation P from here, and here I'll get empty clause. So like through induction, I've proved the completeness. So now Manan will take and he'll give a more
Thank you,
formal
Lavesh.
proof.
Manan.
Am I audible? Can any online participant confirm if I'm audible?
Yes, you are audible.
Right. So I'll be presenting an alternate proof that goes through stone duality. That's, I suppose, a cleaner proof than the standard ones, but it's also heavy machinery. I'll be assuming that we are familiar with the fact that the set of well-formed formulas can be reduced to a Lindenbaum-Tarski algebra that is itself a Boolean algebra. So we'll first look into some preliminary results that are needed to get to the proof itself. So let's say I denote the set of well-formed formulas for propositional logic by the symbol script F, and the corresponding Lindenbaum-Tarski algebra I'll denote by A. So how we go from F to A is by using a quotienting relation, where you say that two formulas A and B are equivalent under this relation if they are logically equivalent. So what this means is that A implies B is a tautology. Or I shouldn't say this, or I should say A if and only if B is a tautology. So from the set of well-formed formulas, we move to an equivalence class of logically equivalent formulas, and we observe that this forms a Boolean algebra. I should move to the right a bit. So this gives rise to a Boolean algebra. I furthermore define a partial order in such a manner. Let's say I have an equivalence class of formulas S and another T. So I'll say that the equivalence class of formulas S is less than or equal to T if and only if the formula S implies T as a tautology. So we recall the definition of a filter once again. For convenience, I'm just calling it A, all right. So a filter on A, so definition. A filter on A is a subset of A. Let's say a subset, let's call it F of A, such that first of all, we require that it be non-empty. Second, we want that if A and B are in F, then they meet B and F. I suppose we're already familiar what the meet operation corresponds to in the Lindenbaum-Tarski algebra. In our case, it's going to be, as was mentioned in Professor Banerjee's lecture, this corresponds to following. Now, if A is in F and A is less than equal to B, where it is understood that the relation is as the one I described before, then B is in F. So this is the definition of filter that we're going to be using. We also recall a proper filter is obviously it's proper if F is not equal to the entire thing, F is not equal to A. And it's furthermore a prime filter. So it's a prime filter. If first of all, it should be proper. We've already mentioned that it should be proper. Secondly, we require that if A or B is in F, then it must be the case that either A or B is in F. Intuitively, there are no, it's not coming out of thin air. There are some atoms that must belong to our filter already. All right, so the next thing I'm going to define is the set of prime filters. Let's say I have an algebra A, my current algebra. A be my task, it's standard notation. I'll probably not mention it again. So we denote prime filters on A such that set of all prime filters on A. Next thing I'm going to define is so for any particular subset, we can furthermore define the set of filters that end up containing it, the prime filters that contain that particular subset. So let us suppose we have a subset given subset B, let's call it B of A. We have V of A or V of B that we define to be the set of all prime filters. Let's say filters on A such that B is a subset of B. Finally, in case we have a singleton, let's say B is a singleton, we will drop the braces and we'll just call it V of A instead. We'll just keep that in mind. Finally, an ultra filter is, as was already defined, an ultra filter is a maximal filter. Being maximal means that it's obviously not proper, it's going to be a proper filter. Furthermore, any filter that contains it will end up being the entire thing. So there's no proper filter that contains it. And furthermore, in case of Boolean algebras, we have this nicer result, this correspondence between ultra filters and prime filters. So a filter, let's say an ultra, okay, let's just say a filter U of A is an ultra filter if and only if U is a prime filter. All right. I suppose these are a lot of preliminary definitions, but most of the stuff we've already seen before. So I hope this is not a lot of new things either.
You have 2 minutes, Manan.
All right, all right. I'll
just wrap it up.
All right. So we already remember that to every Boolean algebra, we can associate a Boolean space using its topology. So to A, let's say we associate the Boolean space that we denote by U of A. Now I'll just proceed to prove the theorem itself. All right, so the statement of completeness in our case translate to the fact that given sentences S1 through Sn, if T is provable from them, this is one and the same as saying that for all valuations W, valuations is a map, of course, from the set of propositional variables to the set 2. For all valuations W, we have WS1, WSN, if WSN all evaluate to true, or let's say 1, then it must be the case that under the valuation W, T evaluates to 1. This is what we intend to prove as a part of our completeness. So let's denote this by cross. So we make use of the representation theorem, the Boolean algebra representation theorem, or the stone representation theorem. I can probably not set up the exact machinery, but the idea is that given these formulas, conjunction, the right-hand side, essentially we're interpreting the right-hand side, interpreting this in terms of the Boolean algebra formalism, it corresponds to this. Now we claim that our claim is in order.
Your time is up, Manan.
Just a minute, please. I'll wrap this up.
Just say the punchline, whatever it is.
Still, there's no punchline at all. I'll try to wrap this up. Just give me a minute, please. All right. So let's say if W is a valuation, if W is a valuation of propositional logic, then the set UW that we denote by set of all those equivalence classes of formulas that are satisfied by W, or that evaluate to true. And we claim that UW is an ultra filter. It's an ultra filter on our algebra. On our algebra that we were denoting by A. And furthermore, we define an evaluation in terms of U such that.
Manan, please stop now.
All right. I'm sorry I could not wrap this up sooner, but I should just.
It is really very ambitious to complete the proof of completeness in 10 minutes.
I should mention the reference at least. This is an excellent expository article by Marcus. So we can find the proof there with the entire prerequisites that all you need. Stone duality for Boolean algebras.
Sorry, what's the source again? I can't see.
It's an article, expository article by Marcus titled Stone Duality for Boolean Algebras.
Okay, thank you.
All right, thank you very much.
Thanks to both Lavesh and Manan. Let's clap for them. Now, the last presentation of the day. Yeah, that's by Avijit Ghosh and Chandrima Kayal on representations of game algebra.
Yeah, good afternoon, everyone. So I'm Avijit Ghosh. I'll be presenting. We've worked on this slide and we are presenting this. So I'll be talking about how game algebras are represented using extended forms of lattice algebras and all that, distributive lattice algebras and all that. So, and also be sharing quite a good result by the Venema about isomorphism between two game algebra and board algebras. So let's begin. So what is a game actually? So consider you have all now, I'm audible, right?
Yes.
Okay.
Yes.
So yeah. So what is a game actually? So we have been introduced here regarding the first order logic, and there's their models and interpretations as well. So let's consider a game, a very famous game called evaluation game. So consider so we are given an FOL model. So F is the frame, so you can consider it containing all the domain and the interpretation definitions here. And pi is the usual evaluation, and an FOL formula phi. And say your claims, so we'll be playing a game. Say your claim is that this formula phi is satisfied, is true in this model. and my claim will be that this formula phi is not satisfiable in this. So let's play a game. What are the rules here? So you're trying to, so what will be your move? So you're trying to prove, so remember this, you're trying to prove that the formula is true here. And I'm trying to prove that the formula is false here. So whenever the phi is an atom or a predicate, so what you will have to just satisfy, so see that whether phi is satisfiable here, and you win, else I win. Okay. So let's say it's a disjunction of two formulas. So disjunction of two formulas, what does it mean by that? So at least one of these two subformulas have to be true, right? So you choose one of them. You choose one of these subformulas, which you tell that it is true, claim that it is true, and we continue the game with the same claims using that subformula. Similarly, for disjunction, since I'm the falsifier, I'm trying to prove false that phi is false here. I will, for me, at least one of them has to be false. So I will give you another subformula among these two, and say, and we shall continue the game with the same claims with that subformula only. And if there exists, the formula is like there exists x such that psi. So you give me, since you are trying to prove the truth, you give me a domain, an element from the domain, and say you assign, and we proceed the game by assigning x to that value, and with the subformula psi. And similarly, what we did for disjunction, for all, whenever it is for all, I give you a domain and claim that in this value in the domain, and I claim that when you assign this value in the domain to x, the psi, the rest of the psi becomes false. Hence, for all x, psi will be false. So, and in not psi, it's a special case. So not psi is I am trying to prove phi false, and you're trying to prove phi true. Hence, you will have to now prove psi to be false. Now you become the falsifier. I become the prover or prover to who proves that psi is true, and we proceed with the game, switching our claims with the subformula psi. Okay. So I hope no questions here. I think the rules are pretty clear here, because. So let's take an example. All right. So say we are in the given structure is the natural number, and here by natural number I mean we are including 0 as well. Okay. And we are given this formula. There exists x for all y, x less than equal to y. So say you are claiming it to be true, and I'm claiming it to be false. So according to the rules, the first thing is there exists. Okay. So there exists your move. You give me a domain value. So you give me this domain value x equal to 3. Okay. So you're saying that when I appoint x 3, assign 3 to x, we move on with the rest of the formula, which is this for all x, y, x less than equal to y. The whole formula will be true. Okay. So now my the next move will be mine, since the first thing is now for all, right? So we move for the for all, and I give you 1. And you are left with and we are left with this formula, which is a predicate. So remember, x is assigned to 3 and y is assigned to 1. Then when a predicate comes, you evaluate and find that 3 less than equal to 1 is not true, and I win. But the question here is not how the particular game is played in one instance. The question here is, was there a possibility of you winning? Okay. The question is, well, could you win in that? What if you chose x equal to 0 in the first place? Then you could have won, and you should have won, right? X equal to 0, and I won't find any thing else that contradicts this claim in through y, right? So as you can see, this game, as we call it, goes along. So indeed, you had a possibility. Well, in other words, we say you had a strategy that could have won whatever possible moves I had made. So as you can see, this is proceeding as a tree. So in the first place, you moved for the there exists part, right? You gave me a value. You could have given me many values from n, right? And then from each of these nodes, I start moving because there was a for all there, right? And there I could have given you many values, right? Now, what is this? So what do I, but when you choose x equal to 0, this move, when you choose this assignment, for any move I take, I will end up losing. Hence, you will end up proving that it is indeed satisfying. It is indeed true in this particular structure, right? And I guess everyone is clear with this game and all. What is game? No questions? Okay, so we move. So this is the basic definition. We are dealing with two players called 0 and 1. Now, what is a game board? A game board is the objects as we call states or positions. So in this game, we could have been in different positions, right? You get different states of the game as the game proceeded. So this game board consists of those. Okay. And now with any game G, each player I, we have a relation, which we call a forcing relation or an outcome relation, whatever you call it. So it states that playing the game G, it takes one position from B and gives you a state of positions. And what is it interpreted as? It is interpreted as say for example this expression PRIGT. It says that starting from the position P, while playing the game G, I has a strategy to reach a state of the game or reach reach some states in the game which will be contained in T. So say here you had options while x equal to you reached these states, these three states. So your forcing relations would be maybe starting from this position, you would be set of positions of this state or maybe a superset of it. As long as this,
you have 2 minutes left.
Okay. So yeah, so this is the forcing relation, and by the way, Chandrima won't be presenting. I will be presenting the whole thing.
Then you have 15 minutes in total, so you have 6 minutes more.
Yes, exactly. Okay, thank you. So yeah, so this is the interpretation how we interpret this forcing relation RIG. No questions, right? Okay. Now, this is an obvious assumption or restriction. So so whenever you consider T to be some outcome relation from some position P, and U is a superset of T, then U will also be an outcome relation, because you are saying that there are some positions contained in T which I has a strategy to reach to, then every superset of T will be there. Okay. Now, can anyone say what this consistency condition is telling me? Say, so let me say, since there is no time, so let me, so remember that you had, we were like evaluating this formula on this structure. So you can, as you can imagine, if there is a strategy for you to evaluate this formula to be true in this structure, you can say that yes, this model satisfies this structure, right? And if I gave you some false formula which is never satisfied in the structure, I would have won. Okay, I would have had the strategy to win. Okay. Now, see what is this condition is telling you, that if you had the strategy in this game from starting from the start position to reach in a to prove that to reach in the states where it was proven that the formula is true in the model, then I won't have any strategy from the start position in this game to prove that the formula is false. And this is exactly what model consistency means, right? So that is why this is called consistency, and this is why the restriction is given. Okay, else if this restriction was omitted off, you could have proven the same formula to be true as well as false in the same model. Okay, so now what is the game operation? So given two games, what a player can do. So given two games G and H, a player I can choose between two games to play between two games. Dualization. So given a game and you are so minus G is the game where we switch our roles as we did in negation psi case. Also, there is some composition which is called given two games GH. G dot H is we finish playing G and then we start playing H from that point. Okay. Now, We'll come to this definition later. So yeah, so how are so given B, how can you produce this board algebra, say this algebra of games and board algebra games and all that? So board algebra. So here, so B will be this thing, power will be equal to the power set of B cross PB. So this produces, okay, so this produces something of this sorts. These kind of tuples, I guess, right? And this is actually the kind to replicate the forcing relations. So, but not all tuples will be in this thing, right? Because we have those restrictions in mind. So what we do, we take this restriction over OMB, where we take all the tuples which are monotone outcome. So monotone, so maintains that superset property. Then we take this OB cross OB. Why OB cross OB? Because each game will contain relations for I to I and also 1 minus I, right? So this will produce a complete description of one game played, right? So that's why we are getting OB cross OB. But again, OB contains all the sets. So GMB will be all the pairs of monotone relations, right? Now another restriction is left out, which is called the consistency relation, which is now we get the GMC. We restrict we throw away such tuples which are not consistent, and we get the GMC, right? And we have these operations on it, and thus we define the formula. So what is it operation? So two games, say two description of games there. So this is the choice. So if it is a choice, so you the first player will be choosing between R1 and S1, but R2 and S2 will be for all player. And similarly here, the minus is where they switch their roles, and this concatenation, which is composition and all. So now we define the algebra. So this is the full outcome algebra of B, where you have this union over the games and intersection, and over this set monotone sets of pairs, you have the full monotone outcome algebra. Then you have the full board algebra, which contains of all these pairs of monotone and consistent pairs. You have the game union, game intersection.
Avijit, you have less than 2 minutes. Please
okay.
wrap up.
And concatenation. So what is this? So in short, you can say that two games are equivalent if these outcome relations of these two games are equal, right? In this class of algebras. Now another way to see about it is a game algebra. So I'll try to go fast here. So game algebra is so it's like you have a few games. So you have these laws. So you can see that these are actually up till this. You can see that these are actually De Morgan lattice, these laws. And then you perform, extend it with concatenation, and you get our game algebra. Okay, so this is the game, the De Morgan lattice, as you can see, and then you extend with this operator of composition, and we get game algebra. And now the main theorem that was proven by Ida Venema was that every game he proved this isomorphism relation, that every game algebra can be represented using a board algebra, unique board algebra, and vice versa. So now we see this new kind of game which is called concurrent games. I will just rush over it. So concurrent games is actually given two games G and H. So how this G cross H is played? So G cross H is played is actually I plays G and H is parallel. This is how it is interpreted. And I'll rush over this part. If anyone has any question, they can contact me later. So this is what G cross H means, that I plays G and H. And hence, as you can see, this particular operator is coming into play. And also this meaning of this forcing relations, the outcome sets gets a change a bit because of this parallelism and concurrency introduced. So what we do is this is the now, as previous it was set it was
your time
yes,
is up.
Yes, I'm wrapping up. I just have to start. So so for example, if A is a outcome set from some position, it will be subset of B, right? But here for this concurrency, we have raised it to the subset of power set of B. So it's actually containing sets of B. And so it is read like if you land, from position P, I land this outcome relation. So it is read like this. It will land in 1 or 3 or 4, 1 and 3 and 4, or 2 and 3 and 4. So it is read like this only. Okay, these are the semantics. We have there's a paper by Sujata Ghosh and Van Bentham. They have worked on concurrent games. These are the semantics they have given, because the semantics had to be updated a little bit to counter this lifting over the sets, over the power of using the outcome relations. And this is the semantic given for the parallel or concurrency between games. Okay. Now the open question, and I'm ending this with the open question here is: can similar isomorphism or representation can be found when you extend this whole algebra using this cross with this cross operator, right? So can we have a board algebra? Can we have a representation of a board algebra where this parallel game is played, and another set of game algebras and new axioms here? You extending that game algebra with this cross operator, and can we find an isomorphism between them? Also, yeah, what are the axioms when the game algebra is extended with the cross operator? So not just you just don't just have and or dot and negation. You just you also have the cross operator. And do you what are the axioms? How this operator plays with the other operators? This is remains to be investigated. So with this, I thank you all for taking my time. If you have any questions, you can ask away, or you can mail us. Yeah, thank you.
Thanks a lot. So we have had like our student presentation session was really very good. Yeah, I mean we don't really expect students to come up with such nice talks in a very short duration of time. They just got 2 to 3 days to do this, to prepare this talk. So can I ask Avijit to stop sharing, please? Yes. And we'll start our closing ceremony in a few minutes. So those who are available online, if you wish to start your video, yeah, please do. Yeah, we'll just prepare the room for that, and then we'll start. Thanks a lot. We'll get some chairs here.
We don't have that many people, right? Many people. I see.
Just ask them who people to speak and
So are you asking for the distribution of the certificate?
Yes, that channel. So something will happen. Yes. It's the other mic.
Okay, so I'm starting. Okay, so good evening, all. So it's really a pleasure to have all of you throughout that journey of ISLA, and I'm really very much grateful to our Dean of Student Affairs, the DOSA, Professor Siddhartha Pandya, to be here as a chief guest for this closing ceremony. And I would like to I'd like to tell you some few sentences about the birth of the ICLA and ISLA. Actually, Professor Rohit Parikh from City University of New York first proposed to organize a logic conference in India, and they started it at IIT Mumbai, and then they observed that there were very few submissions from the Indian participants in that conference. And then he came up with another proposal to organize a school on logic in India, because there were our community was not that much aware about logic, especially in computer science and mathematics, I should mention. So that's how that ISLA and ICLA came in picture. And nowadays it is becoming like every alternate year, one ICLA and one ISLA used to be organized. And we are really very much happy to get that opportunity to organize ISLA this time. And this time our focus point was to somehow, like, of course, after that also logic in mathematics community was not much popular. So me and my partner in crime, Amit, who mentioned it actually, we thought to popularize that mathematical logic in that community. And we sketched this kind of, what can I say, that schedule and those programs in the, for this ISLA. And to us, I guess that it's a success, because we wanted as many as participants, but whoever joined us previously will walk along with us till the end, and we got really lots of participants at the end as well. And that's it from my side. And now I would like to invite Professor Siddhartha Pandya to say something about that program. Yeah.
I would like to take this opportunity to congratulate the organizers of this week-long short course on account of this 9th edition of ISLA. And my best wishes to the organizers and also to the community to take it forward, so that we'll get to see many more editions of this particular the short course. And of course, thanks to all the participants who joined this event from outside IIT Kanpur. And this hybrid nature of this event has added to the participation. And of course, this also adds to the vibrancy of any academic conclave. And I wish all the participants the very best. And I hope, and I'm sure that you have learned a lot from this weekend, from this week-long deliberations. And again, I would like to congratulate all the organizers and the participants for a successful conclusion of this event. Thank you very much.
Thank you so much for your kind word towards our organization. And now I would like to request our participants to share some of their view, both from online and offline, if they have some.
Yeah.
Yeah.
Our participants as well as speakers, if they have
speakers
anything
as
to
well,
say.
yeah.
Yes. Nitish, please.
And I am really I'm really glad that I got to attend this event. I have no formal training in logic except I attended some lectures. I don't have any courses back at my institute, and all I have, I joined from the first ISLA, and then I got contact with the people and the professors, and I've learned a lot from them. And I always wanted to to get in a community that knows these things, and they are passionate about these things. And these people are more than passionate, and I'm from outside institute, and I didn't feel, especially because Amit sir and Puvita ma'am, it was, everything went so smoothly. So it has been an event that I will remember for a long time. And I think that everyone enjoyed it, same as me.
Thanks, Nitish, for such a nice word to us. Anyone else?
May I also?
Yes, Nick.
Yeah, sure,
yes, Nick, please.
Thank you. No, I just want to again join in congratulating you on this, Purvita and Amit and other organizers on this very nice event. I very much enjoyed it. I thought that it was very well thought out because it was kind of centered around one theme, and every talk seemed to be connected to each other and almost like a continuation of each other. So that was also kind of well thought through and well organized. I also enjoyed today the student presentations. Yeah, I think this is a good tradition that would be good to keep up with. And yeah, and finally, the only thing is I hope that one day I'll be able to attend such a conference in person in India. But for now, I think this online or hybrid format also worked very well. So thank you all once again for this very, very nice organization.
Thanks a lot, Nick. And we also hope you sometime here with us in person, of course. Anyone else? Okay. So if not, I would like to say one thing, I already told that each year, alternate year, we used to organize ISLA or ICLA. So for the next time, ICLA will be at IIT Indore. So I'm just going to share it. That will be the 10th edition of Indian Conference on Logic and its Application. And there you can submit your paper, whatever you work on related to logic. And the deadline is 2nd October. So we are planning to share the link, and the website is already there. And we are planning to share the link by mail. So you will get all the information there. So that's it for the next ICLA. And now I would like to invite our honorable chief guest to distribute the online certificates.
Our technical backbone, Anay, has worked really hard to set this up last night. So with just one click, all the participants will get their own certificates.
Yeah.
Yes,
so
please.
Please, yeah.
Yes.
Okay. Thanks a lot, Professor Siddhartha Pandya. Okay, so now it's time to give vote of thanks. I would like to
say something.
Oh, Dipankar wants to say something. Okay, please, Dipankar.
Well,
Continue.
so I don't know whether this has happened ever in past that a student has been given an opportunity to speak before an international audience. So this is really new to me. So thanks to the organizers and team of ISLA. Well, so I have delivered talks on category theory, which was not quite related to logic, but I feel that it sort of acted like a bridge between these different patches that were taught earlier, and then categorical logic somehow collected all of them together, and by equivalence you saw all of them playing all together. So I was really happy so that you could really enjoy this via the language I taught you. Thank you.
Thanks, Dipankar. Now I would like to invite my partner in crime to give vote of thanks.
Thanks,
Yeah, please,
Purvita.
Amit.
Yeah. So can we get the screen here and the participant screen? Participant screen. Can we get? Yeah. It's better. Sorry. Let's go to Zoom. Yeah. We just want to see. Yeah. Yes. Thanks. Okay. So this is always the last, as I mentioned in my email last night, that every journey must come to an end. And we started with the inauguration session by the Dean of Academic Affairs, Professor Shalab. And we are ending with the Dean of Student Affairs. We are really thankful to both the deans as well as their teams. The Office of Student Affairs has been really helpful. Because of this unprecedented COVID situation, the hall allocation and hall allocation committee that has it took our special request to host 3 to 4 participants on campus. Otherwise, I mean, we were hanging in the air until Saturday, last Saturday. What will happen? These people had said that they are coming to the campus and we did not know where we are going to accommodate them. At the end, we are ready to keep them in our, invite them to our houses. Yeah, this especially, I mean, apart from the dean, the associate dean of hall affairs, the assistant registrar, Manoj Kumarji, and of course, the chair, council of wardens, yeah, Professor Saurabh Mani Tripathi. Yeah, all of them have helped us in getting this, making this accommodation possible, as well as the hall 1 staff like Manish ji. We can't forget the LSC staff, especially Neeraj ji and Amit ji, for always being there, just a call away or just a shout away. Then we have had the main thanks goes to the participants. Yeah, some of you have traveled in this hot weather, yeah, to the IIT campus and survived here for a week. So definitely you are worth congratulating just for that reason, because you are not used to this kind of weather earlier and you came here just for this reason. Yeah, that shows your dedication and determination to learn. We are, of course, thankful to all our speakers. Yeah, especially the speakers who are not here, not on campus. I don't think Professor Mahua Banerjee could be here today. No. But Professor Sujata Ghosh, Nick Bezanishvili, and Marcus Tressel, and our 2 student teachers. Yeah, that's an odd combination to say. But Dipankar and Animesh have been a great help, especially for me. And the confidence that I had in both of them, they have proved it to be worth. We, of course, got help from various tutors from different institutions like Avijit, Chandrima, then Rodrigo and Soeren, and Bidhan, and our own Bidhan and Prasenjit. Well, Prasenjit is also our organizer. Yeah, so he did a dual job. And anybody else you can think of? Yeah.
That's all about the tutor.
Yes, there is one more person we would like to thank, especially that's Professor Prasenjit Roy. He helped in organization as much as the organizers did. Yeah, he was part of every single decision-making process. So we are also thankful for him and our families who have made smooth conduction possible. We are not paying attention to homes at all right now.
No, especially I'm really thankful to auntie and my mother. Like,
yes.
In execution of serving the drinks.
Yes.
And all. Yeah, we are so good.
Right. So
they never complained and they always helped us.
And finally, I would like to take this opportunity to thank our organizing team. Yeah, Anay and Prasenjit. Especially Anay has worked really hard for the past week.
the day one.
From day one, yes. We have been organizing this for last 6 months. And earlier it was meant to be only online, but then we switched to, when the institute opened, we switched it to the hybrid mode. But then we also warned the participants against coming here because the temperatures were going to be high. So all in all, like, yeah, it's a nice conclusion to this event. And thanks to all. And also thanks to the information and media cell. Yes, Girish ji and Thapa ji.
Yeah.
Yes, Ane, please.
Thank you, sir. So, sir, first of all, in January, I guess, he told me to like, would you want to come and organize this one? Then I was like, yeah, I can do it. And then the motivation was mainly because of the hybrid mode or the online mode of this teaching and all, because I'm very a big fan of online mode, because people from the various parts of the world can connect together and share ideas using this online mode. So I think there are many bad aspects of COVID, but one thing COVID has guaranteed us that we can now do things what we could not do before, like share ideas through various parts of the world. And like, yeah, this should not stop. Like hybrid mode or online mode should not stop, and it should grow. Then only we can share ideas and grow. So yeah, that's it. Thank you.
So once again, thanks to our chief guest and all the participants. Thanks for making this event a success, and hope you have learned something and you will learn more on your own to fill up the gaps.
Amit, can I say something?
Yes, Sujata, please.
Yeah, I just, from all of our participants and all of us, I would like everybody to switch on their audio and give a big clap to all the organizers, please.
Oh, wow. That's great. We are honored, seriously.
Yes. Thanks a lot, Sujata.
Thank you very much.
Thank you. So let us call it a day, and let's hope we meet once again in some event. Thanks a lot.
Thank you.
Thank you.
Thank you all.